Assalamualaikum and a very good day. In this part of the video, I'm going to present a case study on twist beam. Our course code is SEAA3243. We're from section 2. The course name is Theory of Structures. We are from the session 2021-2022, session 2. Let's proceed. We are consisted of 5 members. It's me, Hassanul, and the other members are Ajif, Eva, Clarista, Astalvila, Afika. This is to be presented to T.S. Dr. Hassana binti Abdul Shukur Lim, University Technology Malaysia, Johor Bahru. Table of contents are hereby. First, we will go through the introduction, which is 1.0, and then material and structural assessment, which is 2.0, and then structural design and analysis check, which is 3.0, and then discussion means 4.0, and then the conclusion, which is 5.0. So here is our introduction. We are given the case study that it is located at a classroom of private school in Johor Bahru. It is detected by student elements that support the floor above looked rather out of the ordinary, while the beams are twisted like a snake. It is a form of failure or beams constructed using steel. As we go 2.0, material and structural assessment generally occurs when the shear loads do not act and coincide at the shear center of the beam section. A failure mode happens here due to the lateral torsional buckling caused by an unrestrained beam. And finally, the compression flange and tension flange failed to keep the beam straight and cause a twisted beam.
Next, we will discuss about the structural design with the analysis step. So the first step is we use to assume the number of columns, which is 3 columns in total, which will act as a support on the beam. From the figure, we can see that we have fixed support at point A, pin support at point B, and roller support at point C. The next step is to calculate fixed end moment. For joint AB, the formula that we will use is negative WL square over 12 because of the uniform distributed load with the moment that acts in anti-clockwise direction. Same as fixed end moment at joint BA, but the moment direction is in clockwise direction. As a result, we get the fixed end moment at AB and BA equal to negative 100 kN per meter square and positive 100 kN per meter square respectively. So this step is similar in calculating fixed end moment for CD and BC. So next, we need to calculate the final moment for members AB, BA, BC and CB. We used to calculate for 3 times at maximum, which end at the third balance. As we already know the distribution factor and fixed end moment value, so we can calculate the final moment. As the result, we get the final moment for AB, BA, BC and CB as shown. To calculate the reaction, we need to calculate by span, which start with span AB and followed by span BC. For example, in calculating reaction in span AB, the reaction that acts on the beam is design load of 48 kN per meter, final moment at AB and BA which is 85.75 kN meter and 131.57 kN meter. As we have fixed support and pin support, the reaction that we will get is RA and RB1. As we substitute all values, we will get final reaction of RA and RB1. So these steps is also the same on how we calculate reaction at span BC. So the final reaction at all support are as shown.
Alright, so after we obtain the reactions for every support, which is RA, RB and RC, we need to draw the whole structure of beam with the full reactions and final moments. So from here, we can draw the SFD and BMD. So from the below picture or figure, on the left side is the SFD, which is the shear diagram, and on the right side is the BMD, which is the bending moment diagram. For the next step is, we need to calculate the critical bending moment, which is MCR. Why? Because in this project, we need to know the maximum value of the bending moment so that we know that is the maximum value before it fails. So after we calculate the MCR, from this BMD we can gain the MED, which is these two values, which is MED and MCR, need to compare. What we have obtained from this project is the value of MED is lesser than MCR, which is the value of MED is 131.46 and the MCR is 177.825. So from here we can conclude that our project is adequate and applicable for this case study.
Alright, let's move on to the discussion part. So for the first part is I'm going to explain about the most probable cause of twisted beam. The most probable cause of a twisted beam is the torsion of the beam, which means the beam is not fully restrained laterally. Torsion in beams arises generally from the action of shear loads, whose points of action do not coincide with the shear center of the beam section. In short, torsion is actually the twisting of a beam under the action of torque, which is also known as twisting moment. Torsion in beam occurs due to eccentric loading, which causes primary torsion. What is primary torsion? Primary torsion arises when the structure has no other options to resist the external loads, but a twist. In this case, the only way to resist the torsion due to external load is by the strength of the materials. A simple beam receiving an eccentric line of loading along its span, cantilever or eccentrically loaded box girders are some examples of primary torsions. So the next part is the lesson learned from twisted beam. So in our case, the beam has formed torsion, which is a twisted beam due to an unrestrained beam. The designers should analyze the magnitudes of the torsional effects and consider the bending of the members to resist the torsion. With that, there is an approach to designing our beam by placing columns that indirectly form a restrained beam. This approach is needed to eliminate torsional effects. The designers also need to ensure that the beam is statically indeterminate and stable. Therefore, before designing a beam, all modes of failure need to be considered. If a failure occurs, it will involve costs to repair what the causes have done. Hence, as an engineer, it is more professional to take all the consideration.
Recommendation for buildings that have the same problem. The first is to use web stiffness. So, using web stiffness is to improve the stability of the beam. Although it is not efficient as when we change the type of the beam or its finishes, other aspects are considered to be changed as well, such as the strength. So, a complete overhaul of designing process is more recommended than simply using web stiffness. The other recommendation is to change the type of the beam that being used. Instead of using the general hot roll I section or H section, it is recommended to use hollow steel section as they have more tensile and torsion resistant. It is recommended to use rectangular hollow section for this case. For existing buildings, it is recommended for immediate replacement of the damaged beam to a new one. This is to provide higher quality of strength and resistance. As we improve the techniques and designing process of structure design, we can implement torsion effect resistant shacking on asymmetric beams, hollow section, and also connection design. So this improvement will help in determining the stability of a structure.
As a conclusion, based on our case study, the design analysis that has been calculated is applicable to the problem that we face. Besides, we also came up with the most expected causes of twisted beam, which is due to torsion. Next, we can conclude that professional skills are needed as an engineer to avoid any structural failure that can cause inconvenience to other people or even losses of life. All the factors needed to be considered in designing a beam is to make sure it is stable. Therefore, there are some recommendations that can be implemented, such as adding web stiffness to increase the stability of the beam, and changing the type of beam from hot roll I section or H section that can to hollow steel section, where it can reduce the torsion failure. Last but not least, it will be effective for the beam to be replaced immediately if there is any defect or damage. Hence, our design projects are practical based on the situation.